Green's theorem. First, let's define what we mean by the positive orientation of a curve C around a region D. Suppose we have a simple closed curve C that surrounds a region D, or you could even say that C is the boundary of D. The positive orientation is the counterclockwise traversal of the curve. So if we think about having an initial point here, notice that we can go in two different directions. We can either go in this direction or we could go in this direction. So the positive orientation is when we go counterclockwise. Another way to think about this is as you're moving along the curve, the region would be on your left-hand side if you are doing a positive traversal of the curve. If you go in the clockwise direction, this would be considered a negative traversal, and in this case, as you walk along the curve here, the region would be on your right-hand side. So just remember, positive orientation is counterclockwise. Now I have another couple of pictures down below here. So here we have a region D and a curve C surrounding D. And again, this is a positive traversal because we are moving in the counterclockwise direction. But again, another way to think of it is as we're moving along this curve, the region is always on our left. In the other picture, we have a region D and a curve C, and notice this time we are moving in such a way that the region is on our right-hand side as we move around the curve. So this would be a negative traversal of the curve C, whereas this is a positive traversal. Or we could say a positive orientation here and a negative orientation here. Green's theorem can be thought of as the fundamental theorem of calculus for double integrals. This means that Green's theorem is one of the most important theorems in multivariable calculus. Green's theorem states, let C be a positively oriented, piecewise smooth, simple, closed curve in the plane, and let D be the region bounded by C. So I have a picture down here. So we have a curve C, which is moving in the positive direction, and that surrounds a region D. If P and Q have continuous partial derivatives on an open region that contains D, then the integral along the curve C of P dx plus Q dy is the same as the double integral over the region D of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y dA. So first, it's important to remember that we are basically looking at the integral along a curve of some function f, dot product with dr, where r is a parametric representation of that curve. We already know that this is equal to the integral of p dx plus q dy along that curve. And now we're saying this is equal to the double integral of partial q partial x minus partial p partial y dA on the region that the curve surrounds. And in this case, of course, f is equal to the vector function p of xy, q of xy. So this is, of course, why we have a p and a q here from the function f. And another thing that we can think of is the curve C is the boundary of the region D. And curve C has a positive orientation. And so another way we can represent this is we can say del D, look like the partial derivative symbol here, which is often called del. And so del D is the boundary of D. or it is the curve C in a positive orientation of that curve. So we can actually rewrite Green's theorem to be the following. So we can say the double integral on the region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y is equal to the integral on the boundary of D of p dx plus q dy. Now what you should notice here is that on the right-hand side we have the functions p and q, and on the left-hand side we have derivatives of p and q. This is very similar to the fundamental theorem of calculus. So if you recall, the fundamental theorem of calculus says if you take the integral of the derivative of some function on the interval from a to b, this is equal to the antiderivative of that function evaluated at b minus the antiderivative of that function evaluated at a. The important thing to realize is on the left-hand side we have the derivative of that function, and on the right-hand side we just have that function. And the other thing, this is an interval from a to b. Think of a number line from a to b. And this is simply looking at the boundary of that interval. Because if you're looking at a number line from a to b, the boundary of that interval is simply the points a and b. And so this is basically the fundamental theorem of calculus for double integrals. Now, what's interesting about this, however, is that when we use Green's theorem, we typically do not use the theorem in this direction. In other words, we aren't going to be changing a double integral into a single integral. Rather, we primarily use the theorem in this direction. So we'll be changing the single integral into a double integral. So let's consider this first example. We have the integral along the curve C of x to the fourth dx plus xy dy, where C is the triangular curve consisting of the line segments that connects the points 0, 0 to 1, 0, 1, 0 to 0, 1, and 0, 1 back to 0, 0. So we could integrate this without using Green's theorem. To do that, we would have to find a parameterization for each of these curves. Now, each of these parameterizations are pretty simple. I'm going to go ahead and write those down. Okay, so here are all those parameterizations and their corresponding differentials and limits. And so we have the integral along the curve C of our expression here is equal to the following. You can pause and double check all of these substitutions. But now let's go ahead and evaluate this integral. Okay, so we should get the following here. And now substituting, we have 1/5 here. Plus, here we're going to have 0 minus 1/5. And then for the last integral, we have 1/2 minus 1/3. And if we add all these up, we get 1/6. Okay, so it's definitely doable, but that was kind of a lot of work. Let's see if we could have used Green's theorem to do this problem. All right, so here is our original integral. Notice that we have the function p is x to the fourth. The function q is x times y. Green's theorem says this will be the same as the double integral over the region D of the partial derivative of q with respect to x. So let's go ahead and compute that. Partial q partial x is going to be y. And then minus the partial derivative of p with respect to y. This is going to be 0. And so this becomes the double integral over d of the function y dA. Okay, now let's look at our region D. This is just basic double integral stuff here. If we integrate the function with respect to y first, we can see that y goes between y equals 0 and y equals the function 1 minus x. And then x, of course, goes between x equals 0 and x equals 1. So I'll have the integral from 0 to 1 of the integral from 0 to 1 minus x of y times dy dx. And this is the integral from 0 to 1. Let's go ahead and evaluate this one. That's going to be y squared divided by 2 from 0 to 1 minus x, which is 1 minus x quantity squared divided by 2. And we can factor out the 1/2. And then from here, we can go ahead and do a simple u substitution. And that gives us the following. And then now when we evaluate, plugging in 1, we get 0 minus. And then when we plug in 0, we get negative 1 minus 0 cubed over 6. And this is equal to 1/6. So notice how we got the same answer, but I believe this is substantially less work. So this is why Green's theorem is useful. Now, before we do this next example, one quick piece of information here about notation. When you see the integral and a circle here, this just means that you're integrating on a closed curve, and we always assume positive orientation. Another way to indicate this is sometimes you'll see an integral sign with a circle, and you'll actually see a little arrow kind of pointing in the positive orientation direction, okay? So both of these mean the same thing, and you can see that is being used here in this next example. So to do this problem here, let's go ahead and just go straight to Green's theorem. Let's notice that we are integrating this function or this expression on the curve C, where C is the circle of radius 3 centered at the origin, okay? So let's identify P and Q. P is the function 3y minus e to the sine x, and Q is 7x plus the square root of y to the 4th plus 1. Now to apply Green's theorem, we need the derivative of P with respect to y and the derivative of Q with respect to x. So here we're just going to get 3, and here we get 7. And this integral becomes the double integral over the region D of 7 minus 3 dA. And so this is simply 4 times the double integral over the region D dA. Now let's recognize that our region is this circle, radius equals 3. And so if we're going to integrate over this region, it would make a lot of sense to change this into polar coordinates. So I'm going to have 4 times the integral. Theta is going to go from 0 to 2 pi. And then we'll have the integral. R is going to go from 0 to 3. And then we have r dr d theta, right? Because our function is just equal to 1. And so now we can separate this. We have 4 integral 0 to 2 pi d theta, integral from 0 to 3 r dr. And this, of course, is 4 times theta from 0 to 2 pi multiplied by r squared over 2 from 0 to 3. This is 8 pi times 9/2, which is 72 pi over 2, or 36 pi. Something to keep in mind when you're working out these problems is when you go back to doing these double integrals, remember all the techniques that we've discussed. So we can integrate with respect to x and y, but whenever it's convenient, like when your region is circular or when you have circles involved in your function, for example, it's often very convenient to just go back and use polar coordinates. Green's theorem can also be used to find areas. So let's recall that when you're talking about a double integral over a region D, if your function is equal to 1, this is simply the area of the region D. So what this means is that this right here would have to be equal to 1. So the partial derivative of Q with respect to x minus the partial derivative of P with respect to y has to be equal to 1 in order to apply Green's theorem to find the area. So what does that mean? What are the possibilities for this to happen? So one way for this to happen is I could let P be equal to 0, and I could let Q be equal to X. Notice that if we take the partial derivative of Q with respect to X, we get 1, and the partial derivative of P with respect to Y is going to be 0, and therefore this would equal 1, which would mean that we could then apply Green's theorem. Okay. Now, if we did that, then in here, P would be 0, Q would be X, and we would simply get the integral of X times dy over the boundary of D. And that's what you see down here, the integral of X dy over the boundary of D, which is also known as C, right? And we have the positive orientation of our curve C. But that's not the only choice. I also could have chosen P to be negative y and Q to be 0. If I do this, the derivative of Q with respect to X is 0. Derivative of P with respect to Y would be negative 1, and we would have 0 minus negative 1, and that would give us 1 as well. So if I let P be equal to negative Y and Q be equal to 0, another possibility for getting the area is doing this integral. And finally, what we could do, since both of these represent the areas, we could add these integrals together and then divide by 2, and that's how we get this third formula. Now, you can use any one of these formulas for computing the area, but sometimes this last formula, believe it or not, is actually the easiest one to apply. So here, let's find the area enclosed by the ellipse x squared over a squared plus y squared over b squared is equal to 1. First, let's just sketch a graph of the ellipse. So this ellipse is going to look something like this. Okay, this is A and this is B. And so I need to find a parameterization of this ellipse. What we can do here is let x be equal to A times the cosine of t. Y will be equal to B times the sine of t. And t will be a value between 0 and 2 pi. And this will give us the entire ellipse. All right, so now to find the area, we are going to do the double integral over the region D, which is the ellipse, of the function 1 times dA. Okay, that's how we would do it normally. But now we can apply the formulas that we just discussed on the previous page here. And I'm actually going to use the last formula, which is 1/2. We'll take the line integral on the closed curve C of x dy minus y dx. So if I'm using this parameterization, let's go ahead and calculate what is dx and what is dy. So dx, derivative of cosine, is negative sine. So we have negative a sine of t dt. And dy, derivative of sine, is cosine. So we have b cosine of t dt. Okay, now I'm just going to plug this in. So we have the 1/2 integral from 0 to 2 pi. X is a cosine of t times dy is b cosine of t dt. Minus y is b sine of t multiplied by dy, which is, multiplied by dx, which is negative a sine of t dt. Something really nice happens here. We have 1/2 integral from 0 to 2 pi. Notice here we get ab cosine squared of t minus, but then there's another minus, that becomes plus ab sine squared of t, and all of this is multiplied by dt. And if I factor out the a and the b here, I'm going to have 1/2 ab integral from 0 to 2 pi, and then I have cosine squared plus sine squared left over, but that's just 1. So this just becomes dt. So we have 1/2 ab times t from 0 to 2 pi. So that's 1/2 ab times 2 pi, which is pi times ab. And that is the area of this ellipse. Green's theorem can also be extended to talk about different types of domains. Suppose we have a domain D. that can be broken up into the union of two other domains, say D1 and D2. So D is the whole thing. D1 and D2 are sort of like the parts that make up D. Doing the double integral of D would be the same thing as doing the integral along the union of the curves that surround D1 and D2, essentially. So if I need to, I can break up the boundary into separate curves if necessary. Also, suppose we have a region that is not connected, or I should say not simply connected. So for example, if we have a region that has a hole in the middle of it, we can find the integral of the domain here, right? So without the hole, by simply taking the integral on the outside curve plus the integral of the inside curve, but the inside curve has to be negatively oriented. And that's just a way of basically taking the integral on the whole thing and subtracting the integral on the inside. So as an example, let's evaluate the following line integral. So we have the integral on the curve C, where C is the boundary of the semi-annular region D. So that is this semicircle here, and then we're only considering the points above the x-axis. So the region D is surrounded by this curve, this curve, this curve, and this curve. So in this particular problem, we have P is equal to y squared. Q is 3xy. So del P, del y is 2y. Del Q, del x is 3y. And this becomes, according to Green's theorem, the double integral of 3y minus 2y dA along the region D, or of the region D. And this, of course, is equal to the double integral on the region D of y dy dx. But this is much easier to do if I change everything into polar coordinates. So remember, in polar coordinates, y is equal to r times sine of theta. And we're going to integrate, in this case, theta is going to go from 0 to pi, right? Because theta just goes from here to here. R is going to go from 1 to 2. Y is r sine of theta, and then multiplied by r dr d theta. And then we can separate these. We have the integral from 0 to pi, sine of theta, d theta, multiplied by the integral from 1 to 2 of r squared dr. And so this is going to give us negative cosine of theta from 0 to pi, multiplied by r cubed over 3 from 1 to 2. Plugging in the limits, we have negative 1 minus negative 1 again. Oops. Multiplied by 8/3 minus 1/3. And so this is 2 multiplied by 7/3, which is 14 over 3. And that concludes this video lesson.